Hello and welcome to Electromagnetics 1. This is Lecture 10. Today we're going to be talking about resistance and capacitance. Well, what exactly is resistance? We've seen the concept of resistance before, but just to recapitulate a little bit, resistance is a measure of how difficult it is to push electrons through a material. In other words, it tells you how hard it is to induce currents in a material. Capacitance, however, tells you how efficiently a structure stores charge. So it's a measure of efficiency with respect to charge storage. We'll return and revisit these concepts a little bit later in the lecture. Well, quantitatively, what is resistance? We know from Ohm's law that resistance is V divided by I, or voltage divided by current, and we now have some ways to relate the voltage to the electric field and the current to the electric field. And so the voltage is simply the electric field integrated along a line between 2 points. So the potential difference between 2 points is just simply, as I mentioned, the line integral of the electric field. And the current passing through a cross-sectional area of area S is given by J, the electric current density, or sigma E here by Ohm's law, dot ds. Okay, so the normal component of the electric current density contributes to the amount of current passing through a surface S. And so the resistance is the ratio of these two quantities. So to find the resistance R of a given conducting material, we have 4 steps. The first is we need to choose a coordinate system. That's pretty universal in this course. The second is we're going to assume a potential difference V naught between the conductor terminals. All right, so if we're interested in the resistance between 2 points on a body, we're going to say, okay, let's assume there's some potential difference V naught between these 2 points. Okay. Then what we're going to do is we're going to solve Laplace's equation to obtain an expression for the potential V everywhere in that body, subject to the boundary conditions that the potential at the first point is 0 and the potential at the second point is equal to V naught. Then we'll find the electric field using this equation here, which is valid for the electrostatic case, and we will find the electric current from this equation, the surface integral of our electric current density, sigma E. And then we will find an expression for the resistance, okay? And this resistance simply will be the ratio of our potential difference to our current from this definition. But as you'll see momentarily, the resistance will not be a function of the potential difference that we chose, the arbitrary potential difference. The current here that we found will be a function of the potential difference, so that when we take this ratio, V naught will actually cancel out from the expression for our resistance. This makes sense. The resistance of the material shouldn't depend on the arbitrary potential that we are putting across it. Well, let's look at an example of how we would calculate the resistance of a curved metal bar. Here's the problem. A metal bar of conductivity sigma is bent to form a 90-degree sector of inner radius A and outer radius B and thickness T, as shown in this figure. So we're going to need cylindrical coordinates, it looks like, for this particular problem. Our task is to find the resistance R between the vertical curved surfaces, so the inner vertical curved surface here and the outer vertical curved surface along there. That's the first resistance, R, we're interested in. The second resistance we're interested in just simply is the resistance between the 2 horizontal surfaces that are parallel to the XY plane. So this bottom horizontal surface here and then this top horizontal surface. We'd also like to know what's the resistance between those two surfaces. Let's start with the resistance between the two curved surfaces. So if we look back at our 4 steps here momentarily, step 1, choose coordinate system, cylindrical. Step 2, assume a potential difference V0 between the conductor terminals. In this case, when we want to know the resistance between this inner curved vertical surface and this outer curved vertical surface, these two surfaces are going to be our terminals. So what we're going to do is we're going to set the potential at rho equals A to 0, and we're going to set the potential at rho equals B out here on this surface equal to V0. Now we need to solve for the potential using Laplace's equation in cylindrical coordinates. Well, if we don't make some simplifying assumptions here, this problem is going to become very difficult. So here's what we're going to do. Assuming the thickness T is much, much less than this distance here, then if you will, the width of our conductor, we're going to make the following approximations. We're going to say that the potential doesn't change in the z direction, nor does it change in the phi direction. Why are those two assumptions legitimate for this problem? Well, in the case of the first one, that the potential doesn't change in the z direction, that's to do with the fact that we are applying our potential here. We're applying the potential difference, or I should say we're creating the potential difference between this inner curved surface and this outer curved surface. So we should expect that most of the potential change should be in the rho direction. All right, it should primarily be, the potential should primarily be changing in the rho direction because we're creating a potential difference between 2 points along a line of rho, okay, along the rho coordinate essentially. All right, so that's part of the reason that we can say that the potential change in the z direction is small. And it's also part of the reason why we can say the potential change in the phi direction is also negligible, because more or less the potential at a constant value of rho is going to be the same, just simply because of the way we've applied our field to create the potential difference. Okay, under these two assumptions then, Laplace's equation reduces to the following right here. Right. So our potential, we're going to say, is just simply a function of rho, and it satisfies this equation. First thing we need to do is integrate the left and right sides of this equation with respect to rho. I can multiply through by both sides of this equation by rho and then integrate, and I'll get this expression. So this is my first unknown constant. And then I can divide both sides of this equation by rho. I get this expression. And again, integrate with respect to rho. And integral of 1 over rho is simply the natural log of rho. And we have a second integration constant that pops out. So in between A and B, for rho between A and B, this is the expression for our potential right here. We don't know what A is. We don't know what B is yet, but we know that the potential takes this form. We're going to find our unknowns A and B by applying boundary conditions. The first boundary condition was that the potential along this inner curved surface at rho is equal to A vanishes. In other words, it's equal to 0. And so therefore, 0 is equal to capital A natural log of rho equals A, little a, plus B. This is our first equation. Second equation, we said that our potential at rho is equal to B is equal to V0. So V0 is equal to A, natural log of rho equals B, little b, plus capital B here. So these are this represents a system of 2 equations and 2 unknowns. When you solve it, you find out that the first unknown coefficient takes this form. The second unknown coefficient has this form right here. So now we're in a position to write down an expression for our potential V in between these two surfaces. Okay. Well, in order to calculate the current I, we need to know what the electric field is, and so we're going to apply this equation to the potential that we just determined, all right? Minus the gradient of our potential, V, that's going to be our electric field. And again, for this particular coordinate system, since we don't have changes in Z or phi, this equation reduces to this equation. Just simply have a first derivative with respect to rho in the rho hat direction with a minus sign. And substituting in here for the particular form of V that we have, this becomes minus A over rho hat. Substituting in here for A, it's minus V naught over rho natural log of the ratio of B to A in the rho hat direction. Okay. So this is the expression for our electric field, and it makes qualitative sense. It makes qualitative sense because we have a potential difference between this inner surface and that outer surface. So it makes sense that the electric field should point in this direction, from here to here, in the rho direction, and that's exactly what it does. It isn't constant at rho, it is not constant in rho, but it only points in the rho direction from here to here. Okay, well, let's find our current I using this equation. So we're going to use Ohm's law. J is sigma E, so if we know sigma and E, which we do, we can calculate J. And then we're going to be integrating over a surface S, okay? And the surface S is another vertical surface here. It's another vertical surface here at some value of rho, okay? But it's a vertical surface, a vertical curved surface like this, and you see that the ds differential surface area is pointed in the minus rho direction. So that corresponds to a vertical surface at some position rho. And then we're going to integrate over that vertical surface from phi equals 0 to phi equals pi over 2, and from z equals 0 up to z equals t, right here. That's what we're doing next. So we're integrating this expression, j dot ds, which takes this form, from z equals 0 to t and phi equals 0 to pi over 2. And this is the expression that pops out of that, right? So this is the current. This is the current flowing across that surface, across the surface right here. Okay. Okay, so now we need to calculate the resistance, and we decided that we were going to find the resistance in the last step here by taking V naught divided by I. And if you'll notice, I here is a function of V naught. So when we take V naught over I, the V naughts cancel out, and we get our final expression for the resistance between the inner surface and the outer surface. Okay, step 2, we'd like to know the resistance between the bottom flat surface there and the top flat surface at Z is equal to T. So it's the same game. We're going to assume a potential difference of V naught between the surface at Z equals 0 right here. So we're going to set the potential at Z equals 0 to 0 and the potential at Z equals T to V naught. Now we need to solve for the potential in Laplace's equation in cylindrical coordinates once again with the following approximations. All right. Now we're going to say that the variation in rho and the variation in phi is equal to 0. Okay. Well, again, why is this approximation particularly that partial derivative of the potential with respect to rho is equal to 0? Why? Why can you say that? Again, it has to do with the fact that we are creating a potential difference between two surfaces of constant z, right? So it makes a certain amount of sense that since the potential difference exists between these two vertical surfaces, the electric field is primarily going to be directed vertically, and therefore there's going to be very little change in potential as we move in rho or we move in phi. With those two approximations, again, the Laplace's equation reduces to a much simpler form. The only term that survives here in this more general expression, be sure to look this up in cylindrical coordinates initially. And you can see when you make these two approximations, this Laplace's equation simply reduces to the second derivative of the potential with respect to z is equal to 0. Well, how are we going to solve this equation? We can integrate this equation right here twice with respect to z, and this is what pops out for the form of our solution. Some unknown constant a times z plus some other unknown constant b. Have to figure out what a and b are. Again, we do this by applying boundary conditions. When z is equal to 0, our potential must vanish. And so therefore, setting z equal to 0 here, we get the equation b is equal to 0. When z is equal to t, our potential has to be equal to v naught. So therefore, after setting b equal to 0, we have a times t, substituting t for z. A times t is equal to v naught, and therefore capital A is v naught over t. Now we have a very simple expression here for our potential. It doesn't change as a function of rho or as a function of phi. It only changes as a function of z right here. So we can find the electric field, which we'll need for the electric current density parameter J, by using minus the gradient of the potential, this equation once again. Again, if you have a function that's invariant in rho and phi, this equation simply reduces to minus the derivative of v with respect to z in the z hat direction. So electric field is a vector. We've got a vector quantity here. That's a good sign. Taking the derivative of this expression with respect to z, we get this expression for the electric field. Once again, it makes qualitative sense. Let's look at what the electric field is doing. It's pointing down from plus z to minus z. Okay, so it's directed downwards. Again, that makes sense because we've said the top surface is at a higher potential than the lower surface. So we should expect the electric field to be pointing in the minus z direction, and it is. It's another good sign. Okay, now, in other words, in order to find the electric current I here in amps, we need to integrate the electric current density J, which is equal to sigma E, over a surface. And in this case, the surface is simply going to be one of these flat surfaces here. All right, and ds in this case is for a flat surface, so the normal to the surface is in the z hat direction, and this is the ds parameter. All right, so J, which is equal to sigma E dot ds, gives you this expression. And again, we're going to be integrating now. We want to be integrating over one of these flat surfaces. So that goes from rho equals a to b, and phi equals 0 to pi over 2 once again of this expression. All right, the z in the excuse me, this should read d rho right here. Pardon me. This is a typo. That should read d rho. Anyway, integrating over the phi, carrying out the phi integration is easy. That just gets us a factor of pi over 2, and then we have an integral over the rho variable here, which gets us integral of rho d rho is rho squared over 2, and we have to evaluate that at b and a. And that gets us this expression right here for the electric current. Okay, again, to find the resistance, we have to now take V naught divided by the current. Again, the current we found is a function of V naught, so when you take this ratio, the V naughts cancel, and you get this final expression right here for the resistance between the bottom and the top surfaces for this particular geometry. Okay, let's have a quick discussion now about capacitance. What exactly is capacitance? I mentioned earlier that capacitance is a measure of how efficiently a structure is able to store charge. Okay, I'll get back to that in a moment. Let's introduce the mathematical or a quantitative definition for capacitance. It's the ratio of the charge to the voltage, okay, to the potential difference between the two structures. And the charge here this is based on Gauss's law right here. This is essentially an expression of Gauss's law, right? The charge enclosed is equal to the flux of the electric flux density through some surface enclosing the charge. So for instance, for this particular geometry here, this surface S would completely enclose one of these charge distributions like this. So S might be going out here, something like that. All right. So again, Gauss's law tells us that the flux is equal to the flux of the of epsilon E here is equal to the charge enclosed. So that's how we can use this expression for Q. And then on the bottom, we just have our normal definition for the potential, which is it's the line integral of the electric field along some line connecting these two charge distributions. Can be any line, but it's got to connect the two charge distributions. Okay. Well, how are we going to find the capacitance for any two-conductor system? We have two different approaches that we can use. The first one is we're going to assume a charge Q and solve for the potential V in terms of Q using Gauss's law. The same sort of thing will happen. V will be a function of Q. When we take this ratio, the Q's will cancel out. Right. So option 1, assume Q and solve for V using Gauss's law. That's one option. The second option is to assume the potential V and solve for Q in terms of V by solving Laplace's equation. That's option number 2. Okay, now let me address this issue about the capacitance being a measure of the efficiency of a structure, or I should say a measure of how efficiently a structure can store charge. Okay. If you look at this expression right here, Q divided by V, what this is in a sense saying is that let's say we have we fix our charge Q. Okay, we fix our charge Q. If the potential difference between the two bodies here increases, then clearly the capacitance is going to go down. All right. What that essentially means is that the more potential difference that you need to separate the charges, the less efficient your system is. In other words, if it takes for a given amount of charge, this potential will increase if the electric field, essentially, the line integral of the electric field between these 2 points increases. And so essentially what it's saying is that for a given amount of charge, as you increase that electric field, you're basically increasing the force that these charges are going to feel. All right. And so the harder you have to push them in order to separate them is a metric on how difficult it is, or I should say on how efficient your system is at storing charge. So the harder I have to push them, the bigger this will be and the smaller the capacitance will be. So if I only need a very small electric field in order to separate the same amount of charge Q, that's fairly efficient. I don't need to apply very much energy to achieve that separation. But if I need more and more and more and more energy to achieve the same separation, the efficiency of the system, in a sense, is worse. So that's what capacitance is telling you. How hard do I have to work, in other words, to separate a charge Q? That's kind of the idea, or maintain separation between two charges. Okay, let's look at another example here. This is a coaxial capacitor of finite length L. Okay. It has an inner radius A and an outer radius B. So this is a solid conductor right here in the middle, and we've got a conducting shell out here at rho is equal to B. the positive charges, I should say the inner conductor is positively charged, the outer conductor is negatively charged. So just based on symmetry here, and in between I should say this, we have some dielectric with permittivity epsilon right in here in between the two conductors. It could be free space, it could be plastic, it could be whatever, but it's just some dielectric material between the two conductors. Well, we're going to assume that the inner conductor carries a total charge positive Q, and the outer conductor carries a total charge minus Q, and we're going to say that that charge is uniformly distributed along the length of our capacitor here. Well, again, neglecting fringing fields that happen at the edges, basically we can say by symmetry the electric field when rho is between A and B has to be only directed in the rho direction, basically. And that's just due to symmetry arguments. Essentially, the electric field is going to point from a positive charge here to a negative charge on the outer surface, and it's just going to be directed radially in the rho direction. So we can say the electric field has this form. And then because of symmetry, we can apply Gauss's law. So let's choose as our Gaussian surface a cylinder of radius rho, where rho is between A and B. All right, and it'll be, I guess I should say, it'll be a little pillbox. So it will have a top, a bottom, and then some cylindrical sides like a pop can. All right, but there won't be any flux through the top and the bottom because their ds is in the z direction and our field is in the rho direction. Z dot rho is 0, so no flux passes through those surfaces. So we only have flux around the curved surface right here, which is great because we can do this integration here. So we're going to allow our z variable to go from 0 to L, and we're going to allow our phi variable to go from 0 to 2 pi. And so when we do that integration, what comes out is this, epsilon times the rho component of E times 2 pi rho L. Okay, this rho comes from our ds parameter. And so the flux of the electric current density is equal to the charge enclosed, which is Q. We said that there's a total charge here on this inner surface of Q, and so we've enclosed Q with this particular Gaussian surface. You can solve this equation for the rho component of the electric field, which has this form. It simply goes down as 1 over rho. 1 over rho. Okay, well, now we have an expression for the electric field. Now we can figure out what the potential difference is between A and B using the line integral of the electric field. So I'm simply going to integrate rho from A to B here, minus sign out front, substituting in our form for rho, which is all in the rho direction, or I should say our form for the electric field, which points only in the rho direction. And I'm dotting it with dl, which is d rho in the rho hat direction, and for this particular integration. Just integrating along a line radiating out from the origin here from A to B, basically. All right, so integral of 1 over rho is the natural log of rho, evaluated from A to B with a minus sign, gets us this expression. Q over 2 pi epsilon L times the natural log of B over A. That is the voltage, all right? And if you'll notice, the voltage here is a function of Q, but the capacitance is Q divided by V. So when I substitute this expression for V in here, the Q's cancel out, and I get an expression for, my final expression for the capacitance of this coaxial capacitor is independent of the original charge that we assumed being on it. Okay. So that's one example of how to solve a capacitance problem using Gauss's law. You also want to be sure to practice solving it in the opposite direction by solving Laplace's equation. All right, thank you for your attention, and I'll see you in the next lecture.